But on the other hand, intensity is useful if you ask questions about sound spreading out. For example, if I wanted to ask, if I have somebody shoots a gun, all right? Bang. All right? And out here somewhere, there's an observer, and he hears an intensity of, let's say, 20 watts per meter squared. And let's suppose that happens at 10 meters. What's the intensity that would be heard by somebody who's out here? That's really all I can draw. Over here at 20 meters, what would be the intensity that Pac-Man heard from the same bang, assuming that it spreads out the same way in all directions? The idea is that the energy of the sound wave is conserved, and it just spreads out evenly in all directions, like in a sphere. So, of course, some of it just gets absorbed into the ground, so we forget about that. But the part that travels outward like a sphere. And so something like the energy is equal to the intensity times 4 pi r squared. That's the energy. This is the area of a sphere. So we have some formula like this. The intensity at 1 times 4 pi r1 squared is equal to the intensity at location 2 times 4 pi r2 squared. You see that the fact that there's a 4 pi times r squared to give you the area of a sphere is essentially irrelevant because those cancel. So we can just tell students that the intensity is proportional. It drops off proportional to the distance squared. Or just here, our takeaway formula from this is I1 R1 squared equals to I2 R2 squared. So if this is I1 and this is R1, then I2 is what? I2 is R1 squared divided by R2 squared times I1, which is what? 10 meters squared divided by 20 meters squared times my I1, which was 20 watts per meter squared. So what's the intensity? What's the intensity at the second radius? It's not half. It's what? It's a fourth, right? Because that's 100 over 400, which is 1/4. So actually, the intensity measured by Pac-Man would just be 5 watts per meter squared. So this is kind of interesting, right? The way sound spreads out. But clearly, intensity is maybe not the best way to measure it. So instead, we use something called decibels. What's a decibel? Decibel is an example of a logarithmic scale. And here's the definition. You're like, oh, logarithms. I remember logarithms from the end of Math 121. I loved logarithms so very much. Thank you for bringing them back into my life. I feel more complete mathematically this semester for having had this discussion, yes? No? All right. I'll stop. But the intensity in decibels, you've heard of decibels before, right? Beta is equal to 10 times the log of I over I naught, where I naught is equal to 1.0 times 10 to the minus 12 watts per meter squared. This is just a convention. So this is the threshold of human hearing. So this, going back to these in decibels, the intensity in decibels, this gives us a beta. So here beta was, I can tell you the decibel levels for these different things. Like the decibel level for jet noise was 140 dB. The decibels for rock concert, something like 120 dB. Decibels for a noisy restaurant, I believe, was 70 dB. Quiet radio, I think, was 40 dB. And so you see that scale is much more. There's a great. I'm just reading stuff off table 12.2 in your 12-2 in your book, but there's obviously the decibel is a more useful. Almost it seems more linear to our experience, right? And so with this, what happens here? What happens when you put in the threshold of human hearing? What if you put I equals to I naught? What happens with this formula? What's the log of I over I naught? So log of I naught over I naught, right? Which is what? Yeah. The log of 1, which is what? 0, right? So the way this is set up is that 0 decibels is not quite hearable. Now, let's see here. One interesting example that combines some of these ideas is example 12-13 about loudspeaker interference. But I don't know, I don't want to rush through things. I think that's a good place for us to stop today. If I had more time, well, I will have more time. I'm debating whether or not I'm going to talk about more in this chapter. I think I'm going to stop right here. I would just tell you that interesting things to read about past here would be, well, let me just say this. I'd like you to read example 12-13. And I do think Doppler effect is really interesting, but I want to cover special relativity next class, so that's what I'm going to do. So, thanks, guys. By the way, I probably won't be around Monday, so if you have questions for me, I would encourage